Assalamu alaikum, dear students. Starting from today, we're going to talk about the functions of the combination logic. So far, we talked about the different logic gates, and then we talk about the creating a logic circuit by combining different logic gates. By now, you have to be familiar with the basic logic gates, AND, NOT, OR, XOR, XNOR, etc. So by combining these logic gates, we said that we can create a more complex logic circuits. And today we're going to see some examples how we can create a complex logic circuits by combining the multiple very simple basic logic gates. So this is the chapter that we're going to cover today, functions of the combination logic. And these are the contents for today. So today we're going to talk about the half and full adders, the parallel binary adders. We're going to talk about the comparators, decoders, encoders, etc. So all of these different devices, later we're going to see that they are created by combining the very basic, very simple logic gates that we covered so far. So first, let's recap this logic gate. So if you remember, during the last lectures, we discussed these logic gates. We have the AND gate, OR gate, XOR gate, NAND gate, NOR gate, etc. So today we're going to see that just combining these simple logic gates, we can create a more complex and bigger logic circuits. So for the beginning, let's talk about the adders. So what is adder? So adder is just a simple device that can add the two or more bits together. So here you can see the very simple device, right? So in this case, this is a half adder, right? So it can add the two bits together, so A and then the B, and it will generate the some output. So basically what we have here is, so let's say for example, if you have the A is equal to 0, right, and B is equal to 1, so sum here will be the 0 plus 1, right? So 0 plus 1, which is equal to 1, okay? So that's it. So this is an adder that will generate this output. Or for example, if we change the, for example, let's say that if the input is 1, A is 1, B is 1. So 1 plus 1, if you remember, so if you remember from our first lecture, we said that 1 plus 1 is equal to 1, 0. Okay, so here what happened is that this is 0 is a sum, right? So 0 is a sum and 1 is carry, right? So when you add the two numbers, and if the, you know, that if the this is exceeds the position of this number, then we have the carry bit, right? So this is the carry bit. In this case, the carry bit is equal to 1. So this is the output, 1, 0. Okay, now let's look at the truth table for this adder for this device. So what's happening here? Well, so we have the two outputs, right? So we have two inputs and then we have the two outputs. So let's analyze this. So first of all, we have the inputs A and B. So what's happening here is that we are just doing the A plus B. We know that when the A plus B, if A is 0, B is 0, so output will be equal to 0. So this is the sum here, right? So this is the sum. The sum is equal to 0. 0 plus 1 is equal to 1. 1 plus 0 is equal to 1. 1 plus 1 is equal to 1, 0, right? So in this case, the 0 is a sum and 1 is a carry, okay? And this is the only case when the carry bit is generated, okay? So this is the only case when we have the carry bit, when the A is equal to 1 and B is equal to 1. Okay, now, how to create a logic circuit for this device, okay? So first of all, let's analyze the truth table. And let's analyze each output separately. So let's first focus on the output. Let's say, for example, the sum here. Okay, so this output. Let's focus on this output only. Ignore the C out for now. Okay, so let's look at the input. 0, 0, output is 0. 0, 1, output is 1. 1, 0, output is 1. 1, 1, output is 0. So first of all, what you can do here is, if you remember, you can create a SOP expression, right? So you can create SOP expression for this one. So when the output is equal to 1, when the input is here, 0, 1. So for this one, you can write the X equal to, right? So for this one, you can write A complement B. And then there's another one, output equal to 1. When the A is 1, B is 0. So which means the plus A B complement. So meaning that this output, the sum, you can actually implement using this logic circuit, this Boolean expression, and then this Boolean expression you can convert to the logic circuit, and you already know how to do that. Okay, there is another way, by looking at the output. Look at the output. What does it remind you? So it reminds you XOR gate, right? So if you remember the XOR gate, if you look at the truth table of the XOR gate here, it's exactly same as this truth table, AB and then the sum, right? So meaning instead of this expression, we can implement this output using the XOR gate only. That's it. So we can create this sum output using the XOR gate. Now, so meaning this one we can write as a X equal to, so in this case, not the X, actually this is the sum, right? So this is the sum output. So the X is equal to A, and then this is XOR operation, XOR B. So you have two options to implement the sum here, okay? So this is first. How about the Cout? How about the Cout? Cout, if you look here, it reminds what? If you look, the output 0, 0, 0, 1. So output is equal to 1 only when the A is equal to 1 and B is equal to 1. So A multiplied by 1, A multiplied by B. So this one, as you can see, the output Cout can be implemented using the AND gate. So now all we have to do, we just combine these two outputs here. So the sum is generated by using the XOR gate, right? So this is XOR gate. Okay, so this is XOR gate. And the Cout is generated by using the AND gate here. And then we have the two outputs and two inputs. So the inputs A and B are connected to both of these logic gates. So now we created this is the circuit for the half adder. So now we can add the two numbers together by using this circuit. So let's look at this circuit. I already created this circuit using the Circuitverse. So let's go to our Circuitverse app. Okay, so this is the half adder, but in this case I implemented it using the not XOR, but if you remember, our first expression was, so let me write it here, right? X equal to A complement B plus A B complement, right? So let's change it. Okay, so this is the implementation of the sum using this expression, X equal to A complement B plus A B complement. Okay, so this is a half adder, right? So now let's look how it works. So for example, if you have the A and B, A is equal to 0, B is equal to 1. So let's say the 0 plus 1 is equal to 1 here, right? So, or for example, the 1, A is 1, B is 0. So 1 plus 0 is equal to 1 again. How about when the inputs are 0, 0? So 0, 0, output is 0. If the inputs are 1, 1, so 1 plus 1. So 1 plus 1 is equal to the 0, and then we have the carry 1. So output will be equal to 1, 0. Okay, so we can, in this Circuitverse, there's a good, very interesting feature. You can use that. So for example, here I created the one circuit for the half adder. So I name it as a half adder here, if you look at the top, right? So if you look here, let me show the pen. So here I named my circuit as a half adder. So what I can do is now I can call this circuit from outside of any other any other circuit. So here I have the main circuit called adders. So this half adder here is actually this half adder. Okay, so I'm just using this. If I double click, it will go inside of this circuit again. So this is the adder. So now if I have the input, for example, 0, 0, 1, so 0 plus 1 is equal to 1 here. Or 1 plus 0 is equal to 1. 1 plus 1 is equal to 1, 0, right? So this is sum, this is a carry, and this is the function of the half adder. So this is circuit for the half adder. Okay, so I hope this is clear, right? So now let's go back to our slides and let's talk about the full adders. So what is the difference between the half adder and the full adder? So in case of the full adder, we have the input carry. Okay, so here, this is the only difference. We have the input carry. And this full adder is useful when you want to add more than single bits. Okay, so for example, you have to add in case of the half adder, what we are doing, we're adding only A plus B. So we can add the only single bits, 0 plus 1 or 1 plus 0, etc. Okay, with a full adder now, we can attach this full adder to another full adder. So we can attach the two full adders together and add the 2 bits. For example, the 0, 0 plus 1, 0 or 1, 0 plus 0, 0, etc. So that is why we need a full adder. So full adder here, as you can see, it can take the input carry. So that is the only difference. Okay, now how to implement the full adder now, right? So again, so let's look at the full adder. So in case of the full adder, you have the three inputs, A, B, and then the input carry. So input carry could be generated from the previous addition. So let's say, for example, you want to do the 1, 0 plus, for example, the 1, 1, right? So in this case, for example, here the 0 plus 1 is equal to 1. There is no carry. That's okay. But here, when you do the 1 plus 1, what happens is that the output will be equal to 0, and then you have the carry 1 here. Okay. But what about if you want to do the, for example, 0, 1 plus 0, 1. So in this case, the last two bits you want to add together. 1 plus 1 will be equal to 10, and then there will be the carry 1 here, right? So the carry will be generated. So now you want to add the 0 plus 0 plus 1. So this is when you need this full adder. So you have to do the 0 plus this carry here comes here. Okay, so you have to do the plus 1, and then you get the output. So 0 plus 1 is equal to 1. So there is no carry, so it will be 0. So output will be 1, 0. So 0, 1, 0, 0, 1 plus 0, 1 is equal to 0, 1, 0, right? So this is the output of the full adder here. Okay. Now, how to implement the full adder? So first of all, let's look at this circuit here. If you remember, we know how to do the A plus B, right? So we know that how to generate A plus B. How? Using this expression, this XOR gate, right? So using the XOR, we can actually do the XOR operation. We can do the A plus B. So A, this is the plus B, right? So this is the output of this A plus B. But what's happening is now we have another input, which is carry in. So we can do like this, plus this is a C in, carry in here, right? So this is a carry in. So now we can implement this sum here. So this sum here can be implemented using this equation. Okay, so output of the sum can be implemented using this equation here. Okay, how about the Cout now? How about the Cout? Okay, now let's look at the Cout. Let's analyze the Cout. So what do we see here? So whenever A and B is 1, so A is 1, B is 1, of course the carry will be generated, right? So this is the cases when the A is equal to 1 and B is equal to 1. So from here we can say that Cout is equal to 1 when the A multiplied by B, right? So based on the SOP expression, AB will generate the Cout. Or there are other cases. So for example, this case here, this one and this one, right? What is this case? In this case, we have the output is generated when the A plus B is equal to 1, and then we have the input carry, right? So which means we have the A plus B, right? So this XOR operation is equal to 1, but then we also have the input carry. So this is input carry. So this is a C in. So in this case, also the output will be equal to 1, right? So these are the two cases. So when the A plus B is equal to 1, so 0 XOR 1 is equal to 1, and then we have the C in. So in this case, we will have the output to be equal to 1 here. The C out will be equal to 1. So this is another case. Okay. So now, this is two cases when the C out is equal to 1. So meaning that we can combine these two using the XOR condition. So AB plus A XOR B C in. Okay. So now we can implement this circuit here. So this is the sum. So this is now the full adder. Okay, so what's happening here is this is a full adder, right? So we have the inputs A, B, C in, right? And this is the sum A XOR B XOR C in, and this is the C out. When the C out is generated, when the A is equal to 1, B is equal to 1, or the A XOR B and C in is equal to 1. So this is the only case when the C out is generated. Okay, so now we can implement this. But if you look closely, what do we see here is that this was a half adder. If you remember, this is half adder. So what do we have in half adder? We have the XOR and then one AND gate. And if you look here, this full adder has two XORs and two AND gates, right? So meaning that this is the one half adder, and this one is actually another half adder here. So this is another half adder. So by combining two half adders and then the output of the the first the C out of the first half adder and the second one, it generates the C out for the full adder. So we can create a full adder by combining two half adders. So this is the idea. Okay, let's go back to our circuit verse. So this is now the full adder. What do we have? Now for the full adder, we have the A, B, and then also the input carry. So if the input carry is 0, it will work as a regular half adder, right? So for example, if we ignore the Cin is always 0, then the output of the half adder and the full adder will be the same. You can double click and see the inside how it's implemented. So inside, what do we have is that we have two half adders, half adder 1, half adder 2, and then output of the half adder 1 and half adder 2 is connected through this OR gate to generate the carry bit. Okay, and this is the circuit that used in your book. So this is the same circuit here. Okay, so you can actually analyze how the half adder or the full adder works here, right? So you can change the inputs and see the output. Okay, so based on the inputs, you can see the different outputs will be generated. Okay, now why the half adder is important? So let's talk about that one. Oh, before that, let's see some examples. So this one is just you can do on your own. Just go to here and change. For example, when the input is 1, 0, 0, output will be equal to 1 plus 0 is 1, and the carry is 0, right? So you can try this here. So the 1, 0, 0, so sum is 1, carry is 0. Okay, let's go back to our slides, right? So this is some outputs. Okay, now let's talk about the parallel binary adders. So far we have the half adder and full adder. They can add only single bits, right? So 1 bit plus 1 bit. What about if you want to add the more than single bits? If you want to do the 2 bit plus 2 bit or 4 bit plus 4 bit, in this case we need a parallel binary adders. So next we're going to talk about that.